Within the SLS Advanced Development Office, we're focusing on a 130 metric ton vehicle that will take us to Mars. Now, the next thought is, with that particular vehicle, what enhancements could be done? This particular one is a smaller, compact diffuser. And through the development and test, we're trying to see if it would prove out to give us the performance that we're looking for, but also in a smaller, lighter weight package.
We're building this prototype as a potential add-on for the Space Launch System, SLS, which is going to be one of the largest rockets ever built. And when you do that, there's lots of things you have to consider. One of the things that you have to consider is the fact that the engines that are burning to propel this thing into orbit requires a lot of fuel. And so the large tanks that we have that store the fuel and supply it to the engines have to be drained very rapidly. And in doing that, that is really no different than taking a water bottle and turning it upside down and letting the water drain out of it. If you just turn it upside down, it wouldn't come out nice and smooth. So what we have to do is introduce gas into the empty space to fill the void left by the liquid. So that's called pressurization of the tanks. In order to do that, the gases would come in at a very high rate of speed, actually about a third the speed of sound, if you just had a pipe to inject it into the top of the tank. What we want to do with a diffuser is we want to take that high velocity gas that normally would impinge on the liquid surface and turn it into a horizontal flow that will help prevent the jet from impinging on the liquid surface. We have a workhorse prototype diffuser to test out the concept. While we're testing the diffuser, we're taking lots of velocity measurements and gathering a lot of data in order to determine whether our computational fluid dynamics models accurately predicted the behavior of the diffuser relative to what we're actually seeing in test.